Hi everybody, welcome to the next session on audio coding. This time we will talk about PQMF filter banks and MPEG1 and MPEG2 backwards compatible audio, where they are also applied. So first, let me remind you that we are talking about this first block here, the filter bank. And this filter bank is usually followed by quantization according to a psychoacoustic model. Then we have bit allocation here. Then we have bitstream formatted, and this is then transmitted to the decoder. So the complete transmission chain consists of the specification of the encoding algorithm, the bitstream format, and the decoding algorithm. The ITU, the International Telecommunications Union, takes the approach to standardize everything, all three parts, because it deals with telecommunications where two people communicate with each other, and there it makes sense to standardize both sides. MPEG is more concerned about videos for download and broadcasts and such. So this is more like a central station communicating to many. And hence MPEG takes a slightly different approach. It standardizes only the bitstream format and the decoder and not the encoder, which would be, for instance, in the studio. This is only an informative part, an example in the standard. So the motivation for this approach is to be open for further improvements and to leave room for specific corporate know-how. But that also means that there is no sound quality guaranteed, because that depends on the encoder. So this is an overview of the previous audio coding standards. MPEG1 audio is the oldest. It takes audio sampling rates at 32 to 48 kilohertz and can handle mono and stereo content. It has 3 layers, 1, 2, and 3. And layer 3 is the most advanced and optimized for lower bit rates, and this is also known as MP3. It also has copy protection. MPEG2 audio includes more lower sampling rates at 16 to 24 kilohertz, in addition to what layer 1 to 3 can do. And it also adds multi-channel audio in a backward compatible way. So MPEG2 audio is targeted for lower bit rates. MPEG4, as mentioned, was the first one. It was developed from 1988 to 92 for bit rates from 32 kilobits per second to 448 kilobits per second. And layer 1 is the one with the lowest complexity for cheap CPUs for portable devices like radios. Layer 2 has increased complexity and somewhat better quality, and layer 3 has the highest complexity and also best quality at low bit rates. So the sampling frequencies supported, as mentioned, 48, 44.1 and 32 kilohertz. The main building blocks, as we just saw, is the perceptual model using psychoacoustics, and this is mostly proprietary. Right? It just controls the quantization, and that is up to the encoder how to do it. The filter bank is subdividing the input signal into spectral components, as we saw. More subbands or more lines means more coding gain, and the longer the impulse response, the more we are in danger of pre-echo artifacts, and that's why we need switching, as we saw. Quantization and encoding is the step that introduces quantization noise or quantization error. And the spectral shape of the quantization noise determines the audibility of it, right? So that's why we need psychoacoustics to optimally hide the quantization noise or errors from the ear. And this can be designed to leave encoding methods optional. So basically, again, that's the encoder part. So the different layers have different filter banks and different coding. So the first 2 layers both use a 32 subband filter bank, and this filter bank is a so-called PQMF filter bank, which we already saw last time and which we also see more about in the coming slides. It has a frame length of 384 samples, and for the quantization it uses block companding, 12 samples as a group. And the amplitude of the subband samples is indicated by scale factors. Right, this is kind of like gain factors. You will also see more later about it. Layer 2 has a longer frame length, 1152 samples, and again same filter bank. The quantization again uses block companding, and it uses scale factor select information. The layer 3 is more interesting from the point of view of the filter bank. It again has the long frame length of 1152 samples, and it has a frequency resolution of 576 or 192 subbands, resulting from a two-stage filter bank. In the beginning, it has the same 32-band PQMF filter bank in the first stage, and that is followed by a 6 or 18-band MDCT in each of the 32 PQMF subbands. And that's why we get the total number of subbands to 32 times 6 for the lower number equals 192, or 32 times 18 equals 576 subbands for the second stage. For the quantization, it uses a non-uniform quantization with Huffman coding, and it uses scale factor select information. So here you can see the block diagram of layer 1. It only has this 32 subband filter bank. Here we have the psychoacoustic model. The psychoacoustic model tells the encoder what scale factors to use. The scale factors are then determining the quantization step size for the subbands here. And these are followed then by a linear quantizer, or a uniform quantizer rather. And this is then given to the channel together with a dynamic bit allocation. And this results in the audio bit stream. Layer 3 now has this additional block. It has, after this PQMF filter bank of 32 subbands, in each of those subbands it has an MDCT of 6 or 18 subbands. And that results in 576 subbands, here called line. Sometimes it's called line, like spectral line. Then here you can see the psychoacoustic model, here based on an FFT of length 1024. This is then driving the psychoacoustic model, and the psychoacoustic model also controls the bit allocation in the distortion control loop. And this is the same as before. So we saw that the first stage has 32 subband QMFs, PQMF filter bank. For simplicity, we only take an MDCT, and then we can visualize a 32 subband filter bank with our Python program pyrecplay mdct.py by editing the line for the number of subbands n to n equals 32, and we can run it with this command. And there we will see that we get a very narrow spectrogram because we only have 32 subbands, but it runs very fast because we downsample only by a factor of 32. Right? Means we have a higher sampling rate here compared to a 1024 subband MDCT. We can also listen to a subband by setting the other subbands to 0, and we will hear more than just the tone because the subbands are wider than for AAC. So let's try and correct this typo here. We will hear more. For in this case, here it takes, constructs the filter from the input coefficients as taking the coefficients and appending the flipped version, because X does only need to contain the first half since the second half is symmetric to it. Then it computes the complex frequency response, takes the magnitude of it, and then takes the positive half of the passband of our baseband filter and squares it. And basically then it flips to obtain the negative half, here the flip version, and we know that the positive and the negative half are conjugate symmetric. So here we just add them, take the magnitude, we add them, subtract the desired magnitude that it should add up to, sum it up. Before we sum it up, we take the magnitude here so that positive and negative errors don't cancel. And we multiply it by an array of ones because we want to have this constant to be at every frequency step in the passband. So all over the passband we want to have the same sum. That's our unity condition. So that it basically, when you go back to our condition, we want to have it over a region. So here's the unity condition. We want to have it over this region, omega between 0 and pi over n. So going back, so this is basically the region that we cover here. So this gives us an error number, and then the next one is the attenuation condition, the unity condition, the attenuation condition. So here we want to have high attenuation in the frequency region beyond the neighboring subband. And this is what we find here. So 1.5 times 512 divided by n. So 512 is Nyquist divided by n. So this would be the role of pi. Here's some normalization. And then ATT is the number, the error number for our attenuation in this high attenuation region. So we want to have ATT as small as possible and unity condition as small as possible. Both are positive, so we can just add them together with a factor to get a combined error. So we take a factor of 100 because we expect the attenuation to be very small. And we want it to be very small because that means high attenuation in this region. So now we have a function which, as the input, takes the first half of our coefficients and outputs an error number. And we can now put this into an optimizer, which we can see here. So we just apply our minimize function now to this optim func, right? And then it plots the impulse response, the h, after flipping it here. And then it also plots the frequency response. And we can let it run by just copying and pasting this command here. So now I'm optimizing it. It takes a moment, but now it's done. So here you can see the impulse response. You see it's 32 taps long, so that means 8 times overlap, so quite a lot. And here's the attenuation. We can check for the attenuation here. So this is, let's see, if maybe 15 dB here. And then here we have minus 75. So here we have like 90 dB stop at attenuation here. So that's actually pretty good. But we also need to have good attenuation because this causes aliasing. And that's an artifact which is easily audible if it's not enough attenuated. So that's good. So that 90 dB is actually quite nice. So going back to our slides. So here's what we just saw. So we see we get much better attenuation than with the MDCT. And finally, we should also check the unity condition. So this is something that we didn't need for the MDCT because it has perfect reconstruction. Here we don't have perfect reconstruction, so we need to check it. Right? We need to check if the frequency responses add up to a constant. Otherwise, we get frequency distortions. Right? So here we just take the magnitude of our passband plus the next passband of the neighboring band and see if it's adding up and that's what we do here. Right, so we have the positive frequencies, the negative of the next subband, we add them up and plot them. Right, here we plot the magnitudes. So here you can see it. It should be 32 in this case. And we see indeed it deviates somewhat, from the 32, but not much. So here we have 32.2, so it's slightly below it. Here we get more deviation, so here it goes down to 31.2, so here it's a little bit worse. So that shows that we indeed have no perfect reconstruction. So we actually have a frequency response which is not flat overall, over analysis and synthesis. We have some ripple on it. Right, but altogether it's actually quite good, particularly with the attenuation. So here we have a 4-band filter bank with filter length of 32 taps, hence 8 times overlap, and a stop attenuation of almost 100 dB, almost right after the passband, which is much more than with the MDCT. Yeah, and since we have the same modulation function, we can also take the same structure for the implementation, for the efficient implementation. Here we see the analysis filter matrix again, and most of the entries, the not shown entries here, are all 0. So only the ones on this diamond shape are non-zero, and they consist of the downsampled impulse response at different phases here. Right, here's the phase, and here you can see they are downsampled by 2n, and here on the left hand side you have the delays, which you can factor out using the delay matrix as for the MDCT. Similar for the synthesis, same as for the MDCT, and here same formulation as for the MDCT. The analysis is consisting of the input being the blocks of the audio signal multiplied by this filter matrix multiplied by the DCT, and for the synthesis we have the reverse steps. We have the blocks of the subbands multiplied by the inverse DCT and multiplied by the synthesis filter matrix. So this leads to a very efficient implementation. Yeah, so this is again the basic structure that we saw. And here we can see that we might have problems with aliasing in the cascaded structure. So if this is our current passband, then we know if something is right in the neighboring band, some sinusoid for instance, it's attenuated somewhat and then it's mirrored over to the passband because this neighboring subband boundary is also Nyquist for this subband. So we have this mirroring from here to here. And this basically has the effect that the resulting filters are not so good. So we have side lobes, high side lobes, which are the result of aliasing from the first stage. Yeah. And here you can see this image shows the dark line, the thick line is showing the first stage filter. Here's the attenuation, and then here the small dashed lines are showing the width of the subbands of the second stage. Here you can see a signal which is attenuated in the first stage, but then also aliased over to this element here. So this is the aliased signal, and this appears in subband number 2 of the MDCT of the neighboring subband. Right? So we actually mirror over several subbands. So here, this is the second subband of this MDCT counted from this boundary. This is mirrored into the second subband into this first subband, first stage subband. So, but it also means you know where they came from, the alias components. So if there's an alias component here in this subband, then we know from which subband in this first stage subband it came from. So it came from here. So first subband here, first subband here. And that means we also know the attenuation that this first filter bank had. So we just need to look it up, plug this factor in here, and then subtract it. And then we basically reduce the alias component, or ideally cancel it. So these are alias cancellation butterflies. Here the outer butterfly has very small attenuation factors. Here there's not too much because the filter has good attenuation, but here neighboring subbands are mostly affected. Here you have to also take into account that neighboring subbands have flipped frequency ranges due to the downsampling. And to compensate it, we can just multiply every second subband by a sequence of ±1 to flip the frequency range back, so that we have the correct outputs here. Yeah, let's see some details on the bitstream. Here you can see we have a header for each block, and then we have a bit reservoir. The bit reservoir is important for changing bit rates, but it also causes more delay because the decoder has to wait until all bits arrive before decoding. Yeah, the decoder, basically unpacking, reconstruction, inverse mapping. Yeah, you can see it as a flow diagram for the decoder. This is actually part of MPEG. So these pictures are actually taken out of the MPEG standard. And in the standard for the decoder, all those blocks are described in detail so that an engineer skilled in the art, as they call it, can program it. Right. So here again, same thing. Bitstream unpacking, Huffman decoding, dequantization, stereo processing if applicable, then inverse MDCT, inverse polyphase or polyphase synthesis, and then you have the reconstructed audio. Yeah, here's some abbreviations for looking up. Don't want to go into detail there. Okay, and that brings me to the end of the slides. Thank you for your attention and see you next time.